This is a problem solving demo on network analysis using Kirchhoff's law. In this first example, we have here a circuit, a network having two sources. With 48 volts and a 52 volt source. And we are required here to determine the current in each branch using Kirchhoff's laws. To apply Kirchhoff's law, we need to identify the loops wherein Kirchhoff's voltage law will be applied. And now we can name, start the naming at here as A, B in this corner, and at this junction C, D, E, and F, the junction at the bottom. And we need to identify the currents in the branches. And here, how many branches do we have in this network? By the way, branch, how do we identify a branch? Branch is a connection of a series components in a circuit that terminates in a junction. So let's identify where the junction is. And, C is one junction. Here is another junction, which is junction F. Junction, by the way, is an interconnection of 3 or more branches. So these C and F are junctions. B, it is not a junction. It is an interconnection of two terminals of resistor 0.06 and the battery, so it cannot be considered a junction. So therefore, the 48 and the 0.06 ohm resistor is forming one junction. This is forming one branch. This is one branch, and therefore it has a common current. So this is one branch, and therefore there is a current in this branch, and 52 volt source and 0.04 ohm is connected in series with the 52 volt source and forming one branch. And so therefore there is also a current in this branch, and 1.3 ohm terminates at junction C and F. And so therefore there is a current in this branch. Now let us identify the current direction for the 48 volt source and 52 volt source. We can simply say that these sources will supply current, and therefore our current here is coming from the 48 volt source, and let's name this as I sub 1, and also this is a source, so we expect this 52 volt source to be supplying a current, and let's name this as I sub 2, and this the current at 1.3 ohm, since I sub 1 and I sub 2 are both entering junction C, and so therefore we can say that the current in the 1.3 ohm resistor, since there's no source in this branch, it is going downward. So that current enters is balanced with the current that going out of the junction, satisfying the Kirchhoff's current law. So after identifying the loops and the current and its direction, we can now identify the polarity of the voltages in all of the elements in the network, so that we can, when we apply Kirchhoff's voltage law, we can determine whether it is a voltage rise or voltage drop. For the batteries, it is already identified, the polarity is already identified, and we know that the plate, longer plate is positive and shorter plate is negative. How about the voltage at the 0.06 ohm? We identify the polarity of the voltage B sub 1, let's name this B sub 1, the voltage at the 0.06 ohm. Its polarity shall be based from the current direction in the resistor. Since the current I sub 1 is entering this terminal of 0.06 ohm resistor or the terminal of B sub 1, we can say that this terminal is positive, and it lives at this terminal, and so therefore this is negative. So this is the polarity of voltage B sub 1, and this voltage across the 0.04 ohm resistor, let's name this as B sub 2. And we see that the current I sub 2 is entering at this terminal of B sub 2, so therefore this is positive and this is negative. While at the 1.3 ohm resistor, we can see that the I sub 3 enters at this terminal, and therefore this is positive. And let's name this voltage as B sub 3. And this terminal is therefore negative. The 52 volt battery, this is positive and this is negative. And as we can see, the voltages in all of the elements were identified, and therefore we can now apply Kirchhoff's voltage law. So this is actually what we have analyzed. So these are the circuit above. And, we can now apply Kirchhoff's voltage law. considering a loop, and let us consider loop A, B, C, F, A. So loop A, B, C, F, A. Let's start with A going to B. And the voltage is positive since we leave the positive terminal of the 48-volt source. So that it's positive, a voltage rise. And the voltage at the 0.06 ohm or the B sub 1, we enter the positive and leave the negative terminal, and therefore the B sub 1 is negative. And then from C to F, the voltage across B sub 3, we enter the positive and leave the negative terminal, and so therefore it is negative B sub 3. And from F to A, there's no elements in between F and A and no voltage between F and A, and the loop is closed, and so therefore we have to equate this to 0. So we have to replace B sub 1 and B sub 3 in terms of the current and resistance. So this would become 48 minus the current here is I sub 1 and resistance is 0.06 minus the I sub 3 and resistance is 1.3 equal to 0. We shall place all the unknowns at the left side and the constant at the right side. So rearranging, this is I sub 1, 0.06, its coefficient, plus 1.3, I sub 3 is equals to, and this is our equation. We can now consider this is C, D, E, F, C, and apply KVL from C to D. We have the voltage B sub 2, and that is positive B sub 2 because we leave the positive terminal of the voltage B sub 2. And then at the 52-volt battery, we go through this battery from D to E. From D to E, we leave the negative terminal, so 52 volts battery is negative. Then E to F, now voltage. F to C, we have a voltage B sub 3. And from F to C, we leave the positive terminal, and so therefore this is positive. And the loop is closed, so equated to 0. The voltage B sub 2 is equals to I sub 2, the current passing through the resistance, and the resistance is 0.04. So this is 0.04 I sub 2 plus the B sub 3. The B sub 3 is 1.3. Current is I sub 3. And transfer the 52 volts. At the right side, we have one equation 2. We have three unknowns, I sub 1, I sub 2, and I sub 3. And we need one more equation to determine the unknowns. So to complete the third equation, we can consider the larger loop A, B, C, D, E, F, A. But this would involve more elements in the circuits. To be more simple in approach, you can consider the junction C by applying Kirchhoff's current law. Junction C, the current that enters the junction is positive, and that is I sub 1. Another current entering the junction is I sub 2, positive, and I sub 3 leaves the junction, and so therefore equate this to 0. And this is our third equation. When writing the equation, you have to arrange the variables in order to avoid confusion regarding its coefficients. And writing these three equations in matrix form, this is our first equation. It is first equation. And our equation 2. And our equation 3. Writing these three equations in matrix form. So this is the coefficients of I sub 1, coefficients of I sub 2, coefficients of I sub 3. These are the variables, and these are the constants. The sources 48 and 53 volts. In this demonstration, the approach of determining the unknowns shall use Kramer's rule, but in your own ways, you can determine the unknowns using your calculator, applying linear equations, built-in programs of linear equations in your calculator. However, for purpose of demonstrating manual calculation of of the unknowns, the unknown currents, Kramer's rule is prepared for three unknowns. And the first approach is to determine the determinants of the coefficient matrix. These are the coefficients of the first column, coefficients of the I sub 1, the second column, coefficients of I sub 2, and the third column are the coefficients of I sub 3. So this is the determinants D. And then determine for the unknown I sub 1, get the determinants of the coefficients of this matrix with first column replaced with the matrix of the constant or the matrix of the sources. And then the second and third column remains unchanged. And divide the determinants with the denominator or determinants D. Now, to get the determinants of the numerator, we go first at the main diagonal going downward, multiply these coefficients, and then at the upper triangular matrix, multiply the two coefficients and one at the lower triangular matrix, which is 0. So this makes the value 0. And then the last element in the upper triangular will be two elements in the lower triangular matrix. And that will give you 1.3 times 1 times 52. So this completes the going downward, which are all added and now to be subtracted with all the values going upward. First in the main diagonal, which is 0 because of one of the elements there is 0. And then the lower triangular, two elements. The last element in the upper triangular matrix of which is 48. So that is 1.3, 48. And then the last element in the lower triangular of the right side to the two elements of the upper triangular. And that would result to 0 because of the 0 element. Then all the going downward to be subtracted with all the going upward and to be divided with the denominator D. The determinants of the coefficient matrix would result to the value of I sub 1, which is a negative 24.77. In the same manner, you can also calculate for I sub 2. Replace the column of I sub 2 with the constant 48 and 52 and 0. And the first and the last column remains as is. And then again, calculate first the going downward to be subtracted with all going upward elements. And then divide by the denominator D. And we have here 62.48 amperes. To determine the I sub 3, we can use equation 1 to get the value for I sub 3 by substituting the computed values of I sub 1, and we have here 38.07 amperes. Then we need to check your answer. Check your answer always using the third equation, which involves I sub 1, I sub 2, and I sub 3. When the value satisfies the equation, which is the current law, then your calculated values are all correct. Can you determine I sub 2 instead of using Raymer's rule? Determine I sub 2 using equation 2. Or calculate the I sub 2 using equation 2 after calculating I sub 3 in equation 1, meaning you shall calculate only I sub 1 and solve the rest of the unknowns using the value of I sub 1. That could be possible, but the problem is if you get a wrong value for I sub 1, the rest of your answer will be wrong. So it is better to calculate the values of at least two values of the unknown and then get the third value in one of the equation and check your answer always on the third equation wherein it involves I sub 1, I sub 2, and I sub 3. Now, if you would be using your calculator to calculate all these I sub 1 and I sub 2, you can use the built-in programs in your calculator and you can actually, if you do not know the program, you can ask Google on how to calculate linear equations, and depending on your calculator model, and also the series model of your calculator. This is for Casio, the model series of the FX991MS. I'm not sure if this is also the same procedure in other models. So in this model, you go to equation. So in this model, you go to equation by pressing mode, and press 1. And then the calculator will ask you how many unknowns or number of equations. So you choose 3. So if you do that, the calculator will ask you to input the values in the matrix form. So let's go back to the matrix. So mode, and then press 1, then press 3. The calculator will ask you to input A1, which is actually value. This is the value A1. This is A1. And then when you input 0.06, press equals. So press equals. And then it will ask you the value for B1. Then input 0. Press equals. It will ask you about the value of C1. Then input C1. that is 1.3. Then pressing equals, it will ask you about the value of D1. Press input 48 and press equals. It will ask you about input. Then equals, then it will ask you about D2. Press 0.04. It will ask about the value of C2. Then D2, K3, D3, C3, and then D3. Then after pressing equals, it will give you X value of 24.77. Then press again equals. It will give you the value of Y, 62.84. Then press equals again. It will give you the value of Z. Then press equals 38.07. So these are the unknowns and these are the currents. Here 24 negative 24.77, which is negative. Sorry, this is negative. Negative, yes, negative. You can just scroll up if you want to go back to the previous output of your calculator. So using calculator, it will give you the values directly. And no need for the manual calculation for the currents. My manual calculation of the currents presentation is for purpose of demonstration. Manual determination of current in the circuit. So, in summary, we have a current I sub 1 which is negative. This means that our current direction is wrong, and therefore this current is going downward, or it charges the battery. The battery 42 volts, I think. Like 48, sorry, it's 48 volts. So this I sub 1 is this is from assumed direction. This is it should be going downward. And the value of this is 24. If we use this direction, it is negative 24.77. But if we correct the direction, this is the current flowing downward, which is 24.77 ampere positive. The I sub 2 is 62.84 amperes, and the I sub 3 is 38.07 amperes. So these are the current in the 3 branches of the network. That, as we can see, all the 24 ampere, 38 ampere is supplied by the 52 volt battery, which is the I sub 2 equals to 62.84 amperes.